September 23, 1999. The Jet Propulsion Laboratory, Pasadena, California. Dozens of engineers are glued to their monitors. In just a few minutes, their spacecraft, the Mars Climate Orbiter, is supposed to enter orbit around Mars. 9.5 months of flight, 669 million kilometers, $125 million. The spacecraft slips behind Mars and the signal drops. That's expected. It's supposed to happen. Everyone is waiting for the probe to reappear on the other side of the planet. It never did. Not after a minute, not after an hour, not ever. $125 million turned into a cloud of debris in the Martian atmosphere. And the reason turned out to be so simple it was almost impossible to believe. To understand what happened, we need to go back a few years. In the early 1990s, NASA suffered a major blow, the loss of Mars Observer in 1993. A spacecraft worth nearly $1 billion simply went silent 3 days before reaching Mars orbit. The exact cause was never fully determined. After that failure, and with the rising costs of the International Space Station, NASA adopted a new philosophy: faster, better, cheaper. The idea was straightforward. Instead of one massive, expensive mission, launch several smaller, more affordable ones. Mars Climate Orbiter was one of those projects. A compact probe weighing 638 kilograms, built by Lockheed Martin in Denver, Colorado. Its job was to study the Martian climate, atmosphere, dust storms, and water vapor distribution. On top of that, it would serve as a communication relay for another spacecraft, Mars Polar Lander, which was set to touch down on the surface. The launch took place on December 11, 1998. Everything went smoothly. The spacecraft set off on a journey that would last nearly 10 months. And on the surface, everything seemed to be going according to plan. 2 teams were working on the mission. Lockheed Martin in Denver built the spacecraft and wrote the software for its thrusters. The Jet Propulsion Laboratory in Pasadena handled navigation, calculating the trajectory and managing the flight. Between these 2 systems, there was a critically important data link. Lockheed Martin's software calculated the impulse generated by the spacecraft's small thrusters during what are called angular momentum desaturation maneuvers. That data was then fed into JPL's navigation system, which used it to update the probe's position in space. And this is where the error occurred. Lockheed Martin's software output the thruster force data in pound-force seconds, an imperial unit traditionally used by the American aerospace industry. JPL's navigation software received that data and processed it as Newton seconds, a metric unit. That's what the software interface specification called for. The difference between these 2 units is a factor of 4.45. Every time the thrusters adjusted the spacecraft's orientation, the navigation system received incorrect data. Each individual error was small, but over 9.5 months of flight, those tiny deviations accumulated. The trajectory drifted further and further from where it was supposed to be. And here's what's truly staggering. The error had been in the system from the very beginning. From day 1, for 286 straight days, the navigation calculations were being fed wrong data. And in all that time, no one caught it. Or more precisely, no one followed through on catching it. And this is the most important part of the story, because the problem wasn't just about units of measurement. In the spring and summer of 1999, while the spacecraft was cruising toward Mars, the navigation team at JPL started noticing anomalies, discrepancies between the predicted and actual trajectory. Doppler data didn't match what other orbit determination methods were showing. The engineers discussed it among themselves. They could see something was off, but their concerns never went beyond informal conversations. According to NASA's official report, those discrepancies were never resolved. At least 2 navigators raised specific concerns about the trajectory. Their warnings were dismissed because they hadn't filled out the proper forms to document the issue. The formal anomaly reporting process was never triggered. And then, in the final week before arrival at Mars, things became critical. the navigation team discovered that the orbital insertion altitude could be significantly lower than the planned 226 kilometers, possibly as low as 150 to 170 kilometers. 24 hours before the critical maneuver, calculations showed 110 kilometers. The minimum survivable altitude for this spacecraft was 80 kilometers. Someone proposed an additional trajectory correction, a maneuver called TCM-5, to push the probe further from Mars. The team declined, not because they assessed the risks and concluded it was safe, but because the timeline didn't include an additional correction, and they weren't prepared for this off-nominal scenario. On September 23, 1999, Mars Climate Orbiter entered the Martian atmosphere at an altitude of 57 kilometers, well below the survivable threshold. The spacecraft was destroyed. The signal was lost 49 seconds earlier than expected. Those 49 seconds were the final hint that something had gone terribly wrong. On November 10, 1999, NASA's investigation board, chaired by Arthur Stevenson, released its report. The root cause was the unit mismatch. But beyond that, the board identified 8 contributing factors. Among them, a lack of end-to-end verification of the navigation software, informal communication channels between engineering groups, an understaffed navigation team, insufficient training, and a weak verification process for technical interfaces between project teams and the contractor. One of NASA's senior leaders, Edward Weiler, said something crucial at the time. He acknowledged that the problem wasn't the error itself. People make mistakes. The problem was that NASA's systems of checks and balances failed to catch it. NASA did not place the blame on Lockheed Martin. The agency accepted that the responsibility lay with the system as a whole, with the processes that were supposed to catch the error and didn't. What happened to Mars Climate Orbiter is a textbook example of a psychological phenomenon called diffusion of responsibility. This effect was first described by psychologists Bibb Latané and John Darley in 1968. They ran experiments in which participants overheard someone nearby having what sounded like a seizure. When a person believed they were the only witness, they rushed to help almost every time. But when they were told that other people were also present, the likelihood of helping dropped dramatically. The reason is simple and paradoxical. The more people are involved, the less personal responsibility each one feels. Everyone thinks someone else is probably already handling it, someone more qualified, someone whose direct job it is, and that's exactly what happened at NASA. Lockheed Martin assumed JPL would verify the data compatibility. After all, navigation was their domain. JPL assumed Lockheed Martin was delivering data in metric units. That's what the specification required. The systems engineers, whose job was to oversee how all the pieces fit together, were overworked and understaffed. The navigators who spotted the anomaly figured that if management wasn't reacting, the issue must not be critical, or someone else must already be looking into it. Everyone thought someone else would check, and nobody did. This wasn't malice. It wasn't negligence in the traditional sense. It's a systemic, psychological trap. And the more people involved, the stronger it gets. And here's what matters. Diffusion of responsibility doesn't just operate in space. It operates in every team, on every project, in every company. When an email says, "Everyone, please pay attention to this issue," nobody pays attention. When a bug on a shared dashboard is visible to all 10 team members, nobody fixes it. When a task is assigned to the team, no specific person owns it. After the disaster, NASA carried out sweeping reforms. Unit standardization became mandatory. Verification processes were tightened. Communication between teams was given formal structure. But the real lesson isn't technical, it's human. When responsibility is spread across many people, it often vanishes entirely. The only way to prevent that is to make responsibility personal and specific. Not, the team is responsible for quality, but a specific person signs off that they verified a specific interface. This applies to everyday life, too. If you see a problem, don't assume someone else is already on it. Most likely, they're not. It's your silence, multiplied by everyone else's silence, that creates the catastrophe. Mars Climate Orbiter took just one photograph of Mars during its entire mission. Just one. It was captured on September 7th, 16 days before the probe was destroyed. The photograph is all that remains of a $125 million mission, and of 286 days when anyone could have caught the error, but everyone assumed someone else would.